So, you've been working on that project with the extensive use of objects, right? You know how critical it is to understand Java's heap space and garbage collection.
Yeah, I've noticed some memory leaks. It gets confusing trying to figure out what exactly is being collected and when.
Exactly. The JVM allocates memory for objects in the heap space. The thing is, once an object is no longer needed, meaning there are no references pointing to it, it becomes eligible for garbage collection. But here's the kicker: even if something is eligible, it doesn't mean it'll be collected immediately.
That's where things get tricky. How do we ensure it's cleaned up properly then?
Well, you can force a collection using system.gc, but honestly, that's usually not recommended. The JVM does a pretty good job on its own. Now, let me ask you this. Do you know about different generations, like young generation and old generation?
I've read about them, but I'm still fuzzy on their roles and transitions between them.
Okay, so young generation typically holds short-lived objects. When new objects are created, they first go into Eden space within the young generation. Most objects die quickly there, and only survivors make it to the survivor spaces. If they survive long enough without getting collected, they eventually move to the old generation.
And that's where larger objects end up?
Right. And because moving these large objects around would be costly in terms of performance, they stay put until they need collecting. Which brings us back to why understanding garbage collection algorithms is crucial for optimizing your application's performance. For instance, knowing when and how often full GC cycles happen can help avoid those dreaded pauses.
Makes sense. I guess I need to pay closer attention to my object life cycles then.
Absolutely. Plus, there's also metadata associated with each object that helps the collector identify which ones can be safely removed. This stuff might seem overwhelming at first, but trust me, once you get the hang of it, managing memory efficiently will become second nature. Speaking of which, have you ever looked into the generational hypothesis in garbage collection? It's quite fascinating how it impacts efficiency.
Not really, I haven't delved deep into that part yet. Can you explain a bit more?
Sure thing. The generational hypothesis is based on the observation that most objects either die very quickly or live for a long time. So, by segregating objects into different generations, like the young and old generation, the garbage collector can optimize its operations.
That sounds like a smart way to manage resources.
Definitely. By targeting the young generation more frequently, the collector can quickly remove short-lived objects without having to scan through all objects every time. This reduces the overall overhead and improves performance significantly.
Makes sense. So focusing on younger objects saves time and effort?
Exactly. And since most objects indeed fall into this category, it works out well in practice. The less frequent collections of the older generation then handle the long-term survivors more efficiently.
That's interesting. It seems like a clever strategy to balance efficiency and effectiveness.
Absolutely. It's all about leveraging patterns in object lifetimes to make garbage collection as efficient as possible. Understanding these principles can really help in fine-tuning your application's memory usage and performance.
I'll definitely keep that in mind while working on my projects.
Good call. Now in an essay, knowing these nuances can make a huge difference, especially in complex systems where memory management is critical. Speaking of the different generations, let's dive into the specifics of the young and old generations. Have you seen how they differ in terms of size and behavior?
Not really. Could you elaborate on that?
Of course. The young generation is where newly created objects are placed initially. It consists of 3 parts: Eden space and 2 survivor spaces. Most objects are created in Eden, and if they survive a few garbage collection cycles, they get moved to one of the survivor spaces.
So, objects move within the young generation before being promoted to the old generation?
Exactly. Objects that survive multiple garbage collections in the young generation are eventually moved to the old generation. This transition happens because long-lived objects don't need to be scanned as frequently for garbage collection.
That makes sense. What about the old generation then?
The old generation, also known as tenured space, holds objects that have survived several trips through the young generation. These are typically larger objects or those with longer lifespans. Because moving these large objects around would be costly, they remain in the old generation until they're no longer referenced, and can be collected during a full GC cycle.
So, managing these two generations requires different strategies.
Precisely. The young generation uses a copying algorithm, which involves copying surviving objects from one place to another and discarding everything else. This is efficient for short-lived objects. In contrast, the old generation often uses mark and sweep or mark compact algorithms, which are better suited for handling larger, more stable sets of data.
Got it. So understanding these differences can help optimize memory usage in our applications.
Absolutely. Knowing how each generation functions allows you to tune your application's performance by adjusting parameters like heap sizes and garbage collection intervals. Speaking of garbage collection algorithms, let's talk about the mark and sweep algorithm. It's a fundamental method used in many garbage collectors, especially for the old generation.
I've heard of it, but I'm not quite sure how it works in detail.
Sure thing. The mark and sweep algorithm operates in two main phases: the marking phase and the sweeping phase. During the marking phase, the collector identifies which objects are reachable and marks them as live.
So it starts by identifying all the active objects.
Exactly. The process begins with a set of root objects, like local variables and stack frames, and traces through references to find all reachable objects. Once an object is found to be reachable, it's marked as live.
And what happens after all the live objects are marked?
After marking, we move to the sweeping phase. Here, the collector goes through the entire heap and frees up space occupied by unmarked, i.e., unreachable, objects. This effectively cleans up memory by removing dead objects.
That sounds like a thorough way to clean up unused memory.
Indeed, it is thorough but can be time-consuming if there are many live objects. The sweeping phase is necessary to reclaim memory, but it can cause noticeable pauses in application execution if not managed carefully.
Are there any optimizations for reducing these pauses?
There are several techniques. One common approach is concurrent marking, where the marking phase runs concurrently with the application, threads to minimize pause times. Another is incremental marking, breaking down the marking phase into smaller steps spread over time.
Interesting. It seems like there are ways to make this process more efficient without sacrificing thoroughness.
Absolutely. Understanding these mechanisms helps in tuning your garbage collector settings to balance between performance and responsiveness.